can I start?
Yes, please. It has started.
Very good morning to our Honorable Vice Chancellor, Sir Professor Dr. Biswas Chatterjee, Provost Sir Professor Dr. Pradeep Kumar Sharma, Dean Sir Professor Dr. Anirudh Mukherjee, HOD Sir, Department of Electronics and Communication Engineering, Professor Sandeep Das Sir, and other dignitaries. I, Tisha Jain from Department of Electronics and Communication Engineering would like to take the privilege to declare that this IETE Student Forum of University of Engineering and Management Jaipur is organizing webinar today on machine learning and its application in predictive maintenance. A brief introduction of IETE. The Institution of Electronics and Telecommunication Engineers is India's leading recognized professional society 1953. IETE Students Forum promotes and conducts basic engineering and technical education programs for human resources, and we regularly organize workshops, seminars, model exhibitions, and quiz competitions in the relevant areas to motivate the students. Now I'd request for our Honorable Vice Chancellor, Sir, to give his few words of encouragement. Sir, please.
Sir, I am not able to hear you.
Am I audible?
Yes.
Am I
yes.
audible? Hello? Okay, sorry.
Yes,
So
yes.
there were some problems. Anyway, so on behalf of IET Student Forum of the University of Engineering and Management, UEM Jaipur, I wholeheartedly invite all attendees to this session on machine learning and its application in predictive maintenance. And the speaker, whom you can see alongside me, is Mr. Arnab Biswas, who is representing Carrier Heating and Air Conditioning Systems. Now, about him, about the speaker, he has got 14 years of hands-on experience in data science and machine learning and software development. So he has got expertise in end-to-end ML, DS lifecycle, identification of use case to model development or deployment. He has built ML pipeline and models for predictive maintenance using big data generated by IoT devices, end-to-end designing and development of distributed, highly scalable server-side applications to manage provision of millions of IT devices to manage or to provision millions of IoT devices. So IoT is also something that comes under his domain, I see. Profiling, tuning, redesigning applications for performance, scalability improvements. These are the works by him. He's a contributor to open source projects community, Stack Overflow, DataKind, Jolokia, Hotio, all this he has contributed in. So we, the teachers of IEM and UEM and all the students, we are very eagerly waiting to hear from you, sir. And we will be able to learn something new, I'm sure, for the coming 1 hour. So it's all over to you. I should not take more time. I hand it all over to you, the speaker, sir. The attendees are waiting to hear from you. Thank you so much. Thank you.
Thank you for all the kind words, sir. Before we begin, probably I want to take a pause, and I want to thank the IETF chapter, the University of Engineering and Management, and our sir for organizing this webinar, as well as for inviting me and giving me an opportunity to speak here. So let's start with today's session, which is about machine learning in predictive maintenance. Just to give a little brief about myself, I am Arnab Biswas. I work for the eco-energy business of uh, Carrier Global Corporation. Carrier is a leader in the HVAC industry, heating, ventilation, air conditioning, and the refrigeration industry. And I have around 15 years of industry experience. Out of that, for last 3 years, I'm extensively focused on data science and machine learning. In my current organization, Eco Energy Carrier, I work in predictive maintenance. I deal with data from HVAC devices. So that's about me. And here is the table of content for the day. Um, there are actually two parts of the session. In the first part of the session, we are going to talk about the basics of machine learning. We are going to talk about what is machine learning, how is it different from the classical programming, then different types of machine learning. And in the second portion of the session, we are going to talk about predictive maintenance. So what is predictive maintenance? What are the other different types of maintenance, and how machine learning is being used in the predictive maintenance industry? So let's start. What is machine learning? To understand what is machine learning, we'll pick up an example task. We'll try to predict the price of an apartment in Bangalore. In a classical programming approach, or in the standard software development approach, this problem is solved in the following way. Probably the company who is building the product, they will take help from a domain expert. They may survey the existing apartments in Bangalore, and then they will identify various factors which are contributing to the price of an apartment. The factors could be the area, the size, the number of bedrooms, bathrooms, then name of the builder, all these things. Once they have identified the factors contributing to the price, what they are going to do is they will come up with a list of hard-coded rules. The rule would be something like this: if the area is Indiranagar and the builder is this, and if it is a high rise and the apartment is a 3 BHK, then the price would be probably the size of the apartment into the square feet or something like that. So that's going to be a rule, very specific hard-coded rules. And once they have the rule, they will write an explicit program where they will embed the rules. One thing is, during in all my presentation, or in all the slides, wherever needed, I have referred to this refer to the links. So what I would suggest is, if you find something interesting, you may want you may visit the link and read further about it. Now this is this is the input output of a traditional software. We have already talked about the rules. So initially, based on the domain knowledge, uh, uh, the developer will embed the rules in a program. And once the rules are there, for a new apartment for which we don't know the price yet, we'll collect the data like availability, location, size, society, etc. We'll feed those data to the rule, and what will come out of it is an answer. Answer is what is basically what is the price of the apartment. So just to pause, in a traditional software, we explicitly write the rules based on our domain expertise, and then we feed new data to the rule, and the system gives out the answer. Now, this thing is done in a very different way in machine learning software. In a machine learning software, the first step of a machine learning software is to collect the data. In fact, if I want to build a machine learning software, what I'm going to do is I'm going to launch the product without machine learning. So that's the phase when I am supposed to collect all the data related to solving the particular problem statement which I'm trying to address to. So that's the same thing which we are going to do for our example problem. So what we are going to do is we are going to collect the data for existing apartment data, probably thousands of apartments in Bangalore. We collect all the details of the apartment as well as the price. Just remember here that we are trying to predict the price of a newly built apartment for which the price is not known. But to start with, initially we are collecting the data for thousands of already existing apartment, all the details of the apartment and its price as well. So each row here represents details of an apartment as well as the price. Again, this is the input output diagram. Here, as you see, what we have done, that we have that existing data, and the data, actually the data has two parts. One is the factors which are contributing to the price, the details of the apartments, and then one is the price. Here we divide that, and the details or the factors contributing to the price, we feed them as data, and the price of individual apartments, we feed them as the answers. These are the existing apartments, so we already know about their price. We feed them to a learning algorithm, and then we ask the learning algorithm to discover the rule. So what happens is the learning algorithm scrubs through the data, discovers the rule to predict the price of a new apartment. I'll say let's take a pause here. Let's try to intuitively understand the thing here. So what we are doing is we are getting the data of the known apartments, of the existing apartments. We are getting their price. We are feeding to a machine learning algorithm, and we are asking the algorithm to discover the rule. As you understand, we have not written any explicit program here. The way we wrote explicit program in a classical programming software. Let's try to compare very quickly what is software 1.0 versus what is software 2.0. In software 1.0, based on the domain expertise, we wrote the rule. We, the human beings, we decide how the property price would be decided. We feed it, then a new apartment comes and we get the answer. But in software 2.0 or machine learning, what we are doing is we are feeding the data of existing apartments, including their price, and we are asking the software itself to find out the rule. Okay, so that's the difference. Here the software is finding out the rule for me. I'm not going to write the rules. Now let's familiarize ourselves with few terms which we are going to use during the session. Number one, each row of the data, for us, it's each row of the apartment along with the price is called an observation. The attributes which are contributing to the price of the apartment are called the features or independent variables, and the price is called the dependent variable or the labels. So with the help of the features, we are trying to generate labels. If there is one single slide which I want all of you to remember at the end of this session, that would be this. This is the very basic essence of machine learning. I am going to actually repeat it again so that the thought gets embedded into your mind. What we are trying to do, we are trying to predict the price of a upcoming apartment in Bangalore. What we are doing is we are gathering the data of thousands of apartments, the details of each apartment, plus the price. These are the existing apartments, so we know the price. We feed the data to a learning algorithm, and then learning algorithm generates something called the rules to predict the price of a new apartment. The rule sits inside something called a model. Okay, so the outcome of a machine learning training process, what we have done so far, the training process is a model. Within the model, we have the rules embedded. Now say in my locality, there is a new apartment which has come up. I know the details of the apartment, but I don't know the price. Or the builder has quoted me some price. I really want to see whether the price matches with the standard market expectation. What I do is I take all the attributes, all the details of the apartment, feed it to my model, and my model gives me the expected price. Okay, so this portion of the process is called prediction. So it's a two-step process. First, training, where we are asking the machine learning algorithm to find out the rule from the existing data. And in the second portion, we are using the model on unknown data to find out the prediction or answers. Now, machine learning is a new thing, and there could be a thought that, well, I should always use machine learning instead of the classical programming approach. But that's not the case. Even in today's world, most of the softwares are probably classical softwares or software 1.0. Okay, one thing I should mention, I am using this term software 1.0 and software 2.0. This term is mentioned by a pioneer of the machine learning industry called Andrej Karpathy. I'll recommend you to visit this link and see, read his article about it. Okay, so let's come back. So there are cases actually where ML works better than the classical programming approach. What happens is, say in complex software products, there could be a long list of rules. Those are called heuristics. So there could be a long list of heuristics, which is very difficult to maintain. Whereas, as we have seen so far, that in machine learning, we didn't write any explicit program. We'll see in future that yes, in next few slides, we'll see that there would be code written, but not for the actual rule building portion. We have not written any code there. So that's how a machine learning software is easy to maintain. Number two, say there is a right now, say this coronavirus thing is going on, there is a there may be a recession or may not be, the property prices are going down. So what's going to happen in a classical software product? They have to revisit probably the market, do some survey, talk to the domain expert, and then go back and start changing the rules, change the rules, add new rules, delete rules. They have to do all the stuff. Okay, but in a machine learning system, what we will do is we are going to feed the new data. So we'll collect the upcoming apartments or the new apartments in the market right now. We'll feed it to the algorithm, and the algorithm itself will automatically discover the changes. Okay, so we don't need to manually change the rule. Then comes the third point. Actually, there are set of data, the type of data for which ML performs far better than the complex problems. Okay, so for example, images, the photos, the videos, the movies, the text kind of data. For example, the posts which we write in Facebook, the news, the literature, the tweets, the blogs, the audio, right now I'm talking, right? That's a audio data of type audio. For this kind of data, ML performs far better than normal traditional programming. And the last thing I want to mention is, well, even when we build a machine learning system, actually we learn something new. I want to emphasize on this point with a story. So I read about it in a book called AI Superpowers by Kaifuli. The book is on different topic, but what I want to share is the following. So it looks like in medical textbooks, the stages of cancer are decided based on the number of yes to 3 questions. Okay, the stages of cancer is decided in medical textbooks based on the number of 3 questions. Well, I should say I am not a medical expert, I am not a doctor, so whatever I am going to tell is based on this book. Now, in the year 2018, the year on which this book was written, year 2018, there was a research paper where the researchers, they analyzed and actually identified at least 15 variables which were contributing to identify the severity of the cancer. So then the human approach, medical textbook approach, is based on 3 parameters, and the research approach or the data science approach is probably based on 15 variables. Why is this difference? The difference is due to the limited cognitive ability. So we human beings, we have a very limited cognitive ability. When taking a decision, we always try to find a handful, very limited number of obvious significant features. And based on those obvious significant features, we take the decision. But on the other hand, if we see a machine learning based system or a AI system, there the number of contributing factors, which we call as features, are hundreds, if not thousands. So a machine learning system doesn't have a limited ability to correlate between the features, correlate between the patterns which the features are generating. Now, once we build such a system, we can probably review those features, and what we'll probably see is the features includes not only the human identified traditional features, but there would be some intuitive features, less intuitive features which humans were not able to identify, or which the domain experts probably thought not so important. So those new features, those less intuitive features, those features which probably human never thought about, domain experts never thought about, those are going to be the learning of the human being from a machine learning model. Now let's come to the formal definition of machine learning. A machine is learning when it improves at a task based on experience at the task. So a machine is learning when it improves on a task based on the experience, but without any explicit programming. For our case, predicting the price of a house was the task, and how the task can be improved. The task can be improved if we gather more data, if we gather more data in a regular interval, seasonal interval, and feed it to the model. So as we explained, um, as the recession hits or when there is a peak in the demand, we have to feed the data so that the model tunes itself, and based on that its experience increases, and if the experience increase, it will be better in predicting the price of the houses, so it will improve in the task. um, Let's quickly take a look at about this artificial intelligence versus machine learning thing. This is this is a common trend where everybody claims to work on AI, where probably they are working in machine learning or in statistics or something else. So what is actually AI? The formal definition of AI, okay, this is from this interesting blog. I'll recommend everybody to read this blog. This introduces very nicely about the basic concepts about machine learning. So this blog, as per this blog, artificial intelligence is a quest for developing non-biological systems that exhibit human-like forms of intelligence. Okay, so the stress, basically the stress is on intelligence and human-like forms, right? Now, I can build a system which is as intelligent as human, maybe without using machine learning. So in that case, those applications will lie in this area, okay, where the circle for machine learning and AI are not overlapping. These are the systems which are intelligent, but they are not built using machine learning. And then there would be systems which are built using machine learning, which are intelligent systems. So they are AI systems, but they are built using machine learning. So that's the overlapping area. Most likely the robotics and probably self-driving cars, computer vision, natural language processing based systems lie in this area. And then there would be huge area, huge number of applications which are developed, which probably doesn't generate human-like intelligence. For example, our predicting the house price thing, that's not a human-like intelligence. That's just another software. We are replacing a normal software. So those are the systems which are built which are just a machine learning system. Those are not AI system. Now, as you can see here, there is another circle called deep learning. I'm not going to talk about deep learning or neural networks here. That's going to be a completely different topic, probably for some other time. But what you should know is deep learning is also a subset of machine learning. So if I read a Google paper from Google, and they are claiming that they are doing machine learning, they may be doing actually deep learning, or they may not be. But what we should know that deep learning is a subset of machine learning. Now, examples of machine learning, um, say recommending a video or song. The moment I go to YouTube, it recommends me a set of videos based on a set of songs or videos based on my previous listening history, and they do it quite well. So I should say actually YouTube knows my preference about music more than I know about it. So that's an example of a recommender system. Then say detecting diseases based on X-ray images. This is an example of computer vision. Then for the forecasting company's revenue based on various factors, that's an example of time series forecasting. Summarizing long documents into smaller and meaningful text. That's an example of language processing. So I think there are apps like InShot or something like that. What those does is they read probably a long news article, and then it summarizes the text so that it can be easily and meaningfully consumed by the human beings. And the last thing, this is something very interesting. I'll say you should all read about it. Do a Google search and read about it, GTP3. So this is a language model developed by a company called OpenAI. And so it can do a lot of stuff. Okay, it can probably chat with a human being in a human-like way. It's like a human-like intelligence itself. It can write stories, it can write tweets, it can do a lot of stuff. But what interested me, what I am going to mention here, given with a set of instruction in my language, in human language, it can start writing HTML, SQL, or Unix code. There are a lot of videos around. In the internet. You may look into it. It looks amazing. Now, there are various criteria based on which a machine learning system can be categorized. Different machine learning systems can be categorized. In fact, there are three ways. There are probably three or more ways, but for the sake of the simplicity of the session, we are going to focus only on one criteria. That's whether or not trained with human supervision. While building or training a machine learning model, whether human supervision is needed or not. Now, based on that, we categorize it in three categories. Okay, actually there are 5 categories, but I'm again going to talk about the most important 3 here. First one is supervised learning. What we have done so far, the house price prediction problem. So there, what we did, we wanted to predict the price, but what we did is we collected the data where we have the inputs, the features, and the prices of the existing apartment. We feed it to the algorithm, and that helped the algorithm to learn the rule of predicting the price from the existing data, from the existing price, and from the existing equipment behaviors. Existing apartment details. So this is called supervised learning. Why it is called supervised? The user, as if the teacher is supervising the algorithm to learn. Okay. Next is unsupervised learning. In unsupervised learning, there is no input and output. There is no features and labels. Nobody knows whether to which category, to which bucket, which label the data belongs to. I'll try to explain it with an example. Okay, this is the work I have again referred here. In this work, what they have done is they have taken all the research article about COVID-19 and feed it to the algorithm. Okay, and they predefined the number of categories which the algorithm is supposed to create. What the algorithm doesn't know. There is no label. It doesn't know that this research article is about this particular problem of COVID-19. What the algorithm did, the algorithm categorized all the articles in different categories, different buckets. So all these dots here is a article or a research article, and the colors represents the articles belonging to the same category. For example, the articles which are red, in deep red, they are different from the articles which are in blue. Again, the articles which are in deep red are similar, close to the articles which are in light red. Okay, like that. Now if we go to this page, we'll find out even they have a Kaggle kernel as well. If we'll find out that once we go to each choose one cluster or one bucket, we'll find out what are the common functionalities, common features among those literatures. And again, if I change the number of buckets, number of categories, then again the distribution will also change. All this happens without uh, the developer telling the algorithm how to create the rule. The algorithm itself discovers the rule, discovers the similarity among the documents, and then try to create the clusters. Now, something similar is being used in probably the news sites. What these news sites do is they categorize, they identify the news articles which are similar in nature, and then they tag them. There are other examples. Again, we are not going into those. But what I want to give an emphasis, since most of the audience is from the student community, if you are starting with your machine learning journey, or if you are going to develop a machine learning product in future, probably it's always better that you start with a supervised machine learning problem rather than an unsupervised problem. Unsupervised problems are usually harder to understand and evaluate. What gets evaluated gets improved. In sorry, in unsupervised learning, it's really hard. It really becomes hard to evaluate it. Now, another thing I should mention, often we use the unsupervised machine learning mechanisms to understand the data better before solving it using some supervised machine learning problem. Now comes the reinforcement learning. Reinforcement learning is a completely different kind of beast. Um, the theoretical definition is, there will have an agent for us, which is a robot. The robot observes, the agent observes the environment, and then it takes some action. For example, for this robot, the action would be go close to the water, go close to the fire, or go close to the water. Now, the once it does a action, either it would be penalized or it would be rewarded. For example, here, the robot, when it goes to the fire, probably it gets penalized by 50 points, by deducting 50 points. But when it goes to the water, probably it gets gains 50 points. Okay, so it gets rewarded. Now, after few rounds of going here and there, robot realizes that, okay, going to the fire is not helping. If it has to get more rewards, then it has to probably be close to the water tap. And that's how the robot learns. So this is called reinforcement learning. Reinforcement learning are very popular when it comes to robotics and then playing games. So if you may be familiar with the system called AlphaGo, which has maybe last 2 years or 3 years back, it defeated the Go champion. Go is something like chess. It's a game. AlphaGo is a system built by a division from Google. So they basically were defeated, the software defeated the world champion of Go. If you are not aware of it, I'll highly recommend, there is a movie in YouTube which is freely available, the AlphaGo movie, you should watch. And then the last thing, it's not the last example, this is one of the examples, it's about energy efficiency. So what happens, say there is a shopping mall, and in the shopping mall there are air conditioners. Now I want to make sure that the energy consumed by the air conditioners, even the lighting, etc., all these things is minimum, but without impacting the customer's comfort. In such cases, we are going to use reinforcement learning instead of supervised learning. Now, now that we know about different machine learning things, different broadly the machine learning categories, let's try to focus on supervised machine learning, because this is what we are going to use in the next portion of our session. So supervised learning is again divided in two portions. One is regression and one is classification. So for regression is about predicting a continuous number, a continuous variable. So we were predicting the price of a house. It could be 40 lakhs, 50 lakhs, 41 lakhs, 42 lakhs, right? So it's a regression. When we talk about regression, it's about continuous numbers. So if I want to predict the temperature of tomorrow, predict the temperature for next 7 days, it's about continuous numbers, 40 degree, 34 degree, 36 degree, 26 degree, right? If it is probably the rainfall, it's going to be a continuous number. But now, say, instead of trying to predict a continuous number, what I'm more interested about is whether tomorrow it's going to be very hot or tomorrow is going to be normal. Okay, so I want to categorize every day from tomorrow onwards in 2 buckets. It's going to be hot or normal, or maybe 3 buckets, hot, normal, cold. So in that case, I'm not predicting a continuous number. I'm predicting a distinct value, a discrete value, which is called a category. In our house price problem, it would be something like this, that instead of predicting the price of the house, we predict whether this house is very costly. Well, is this house very costly? Yes, it's a premium category house, right? Maybe that will help to serve the customer segment better. The people who have a lot of money, they may go for the premium category houses, and then few lakhs here and there, few tens and 20 lakhs here and there, they don't matter. And then there would be a category who is probably interested only about the basics of the house, basic kind of house, right? So this categorization is also important. So this is the example about classification versus regression. Okay, we need to remember this. Regression is about continuous numbers. As you can see here, regression is about, these are the dots, these are probably continuous numbers, the price of the houses, and these are the categories. This is one bucket, one type of houses, probably the basic, this is probably the moderate. Okay, we need to remember this. With this, we are kind of done with the first phase, first part of our session. We have gathered idea about the basics of machine learning. And with that, we'll move into the second portion, which is about predictive maintenance. Now, this world is full of equipments. The aircraft has equipments. The train has equipments. Air conditioning system is an equipment with a lot of parts. The water filter, which is there in my house, that's also an equipment with a lot of parts. Now, every equipment, a mechanical equipment, an electrical equipment, or whatever kind of equipment needs some kind of maintenance. And that maintenance, if it gets damaged, it needs to be maintained so that it can be used again. That maintenance itself is a very big industry. Okay. So there are, we are going to deep dive into maintenance now. There are basically 3 types of maintenance: reactive maintenance, preventive maintenance, and predictive maintenance. Okay. So in reactive maintenance, what happens? I'll give an example. Probably say I have a water filter at home, and I use the water filter. Now I continue using the water filter, and only when it fails on a fine morning, I inform the support person. He comes up and he fixes it. Okay, so I inform the support person, and probably after a few days, the support person comes, replaces the faulty part, and it starts working fine again. This approach has one advantage, one disadvantage. The advantage is we are not wasting the part's life. The part which become faulty, we waited for it to fail. That means its life was expired. Then only we replaced it. So we saved money. But there is a problem with it. Problem is, in between for few days, until the support person comes and replaces the part, I was not able to use my water filter. I had to get water probably from outside or some other means. Now think it in the context of aircraft. All of a sudden there is a failure in the aircraft, and that aircraft is not able to fly for next few days. And that will cost a lot of money to the aircraft company, to the airlines. Next is something called preventive maintenance. Now in preventive maintenance, what we do is, like when I bought the water filter, after a year, the company came and they said, okay, we are going to basically provide you something called annual maintenance contract, AMC. As a part of that, what they do is, during every year, each year they come and change some parts of the water filter. Okay, so they don't care whether the part still has some life, whether it's a part can may be used for some few more days. They just come, replace the part, take the money and go, right? So in that way, what happens is we will fully utilize the life of that particular part. Sorry, we will not fully utilize the life of the part, but what we get is a continuous service. There is no downtime in between these two. So as we saw, it has some advantage. Here we are using fully parts life, but we have some downtime. Here we are not utilizing the parts life, and here there is no downtime. Here there would be downtime, right? So predictive maintenance comes somewhere in between. Here what we do, we try to analyze the health of an equipment. We try to analyze the health of an equipment continuously and then try to predict when it is going to fail. So say we find out that this is the day or this is the week when the equipment or the part of the equipment is going to fail. What I do is, as a company, I send a support person before the failure happens and then immediately replace it. I wait for the equipment to not to fail, but to approach the failure. So in this way, we are achieving two things. Number one, we are trying to utilize the parts life almost to the fullest. And number two, we have a downtime, but that's a planned downtime, right? If I know that my water filter will not work for 1 hour for a particular day because it needs to get servicing, I'll be always fine. And that's the same is true for the aircraft industry probably. If we see here that using predictive maintenance, the the cost is actually lesser compared to the reactive maintenance and preventive maintenance. Now, the goals of predictive maintenance, why we are doing predictive maintenance. The goal is we want to predict if an equipment is going to fail in near future or not. That's the first goal. Number two, predict days to failure. How many days are left before the equipment is going to fail, right? And then um, predict the most probable root cause of failure. So if I know that I have this equipment and this equipment is going to fail in next 10 days, probably I have some time, I can schedule a maintenance. And if I know what is the exact root cause, which part of the equipment is going to fail, it's the electrical part, it's a filter, it's something else, it's electrical circuit, mechanical something, and then I can fix it. The service person who is visiting, he will already carry the equipment. So that will also save some money. Sample use cases, these are uh, very specific, like these are few examples. Just few examples. There are thousands of cases where predictive maintenance is being used nowadays, but it gets used in aircraft, HVAC equipments. HVAC is heating, ventilation, air conditioning. Then elevator door failures, say in shopping malls or like high-rise buildings. If the elevator door fails, that creates a lot of problems. Wind turbines, European countries, they use the alternative, use the alternative sources of energy, right? So they are failing. Prediction of wind turbine failure become important. The failure of wheels of train. So if you find, if you just Google about these topics along with the keyword predictive maintenance, you will find out some good documents, freely available documents, which will give you some idea how they are solving that problem. Now, data science for predictive maintenance. Okay, so here it's not that predictive maintenance can be solved only using machine learning. As we talked earlier, predictive maintenance can be solved in a traditional programming approach, in a rule-based approach also. And that's how it was. Predictive maintenance is not a new industry. That's how they had a rule-based mechanism. Using rule-based mechanism, they built some software or system. Using that system, they used to predict the failure of an asset or of an equipment so far. Now we are trying to introduce data science to it. Now, what happens when a business comes to us, to a data scientist, and say that, well, I want to predict the failure of an asset in advance, and I also want to know the root cause of the asset. Well, that's a business problem. That's a typical business problem, because the business problem is linked with money. And they understand, okay, if this problem is solved, we are going to earn some money. The company will earn some money, and probably will add some value to the society. Now, that doesn't make sense. That doesn't sound like a data science problem. In data science problem, in data science domain or machine learning domain, um, we have supervised learning, unsupervised learning, classification, regression. So the first step of a machine learning product development is to convert a business problem into a data science problem. Nobody is going to tell you that, give you, well, this is the data and this is what you are supposed to do. You are going to build a regression model. It's not like that. The business will come and tell you, this is my problem. Can you, and we believe we have some good data. Can you solve the problem using your machine learning things? So just a warning, in general, the industry considers machine learning as a magic wand. And as we'll see slowly, it's not. It takes a lot of work, a lot of hard work to solve a problem using machine learning. So that's going to be the first step. Back to our thing. That's going to be the first step. Then we have to understand the data, gather the data, prepare the data, build the model, deploy model, monitor models. We'll see all these steps one by one. So now, as I was saying, right? So I want to predict the failure of an equipment, and I want to know the root cause of it. How can I solve that problem? How can I make that problem as a machine learning problem? We have already learned about classification. We have already learned about regression. Let's quickly remember, classification is about category. Classification is about whether tomorrow it would be hot, cold, or normal. Regression is about tomorrow's temperature. Tomorrow it would be 34 degrees centigrade or 42 degrees centigrade or 21 degrees centigrade. So in binary classification, we can have two buckets. For example, hot or cold, true or false. In multiple class classification, we can have multiple buckets or categories: hot, cold, medium, premium, basic, and probably moderate, something like that. So actually convert we can convert the predictive maintenance problem in one of these three things, which we'll see. First is the binary classification approach. When we convert the predictive maintenance problem into a binary classification problem, what we basically do, our goal becomes predict the probability of failure of an equipment, say within next 7 days, next 1 week, 2 week, something like that, fixed. So predict the probability of failure of an equipment in next 1 week of time. There could be two states, either no or yes. Yes, the equipment is going to fail in next 1 week, or no, the equipment is perfectly healthy, it's not going to fail. So that's what happens here. Well, one thing I should mention, that from now onwards, I'm going to talk about, when I'm going to talk about predictive maintenance, I'm going to talk in the daily level. Okay, the time scale is a day. So here, probably on this day, an equipment is going to fail, or an equipment has failed, a known case. It's a supervised learning. We already know the equipment which has failed, and we have the data of those equipment. So on this particular day, this equipment failed. Well, now I want to predict whether any equipment fails within this window of, say, 7 days or 15 days. So all the days which comes within this window would be considered to be a failure case. We label them as 1. We put them in a bucket which is 1. Any days of that asset which is outside the window would be considered as level 0, the second bucket. So this is the binary classification problem. As you see here, we are just predicting whether an asset is going to fail in next 7 days or not. Next is regression. So regression is about continuous number, tomorrow's temperature, 42 degrees centigrade or 43 degrees centigrade. So here if the asset is going to fail, if the equipment is going to fail on this particular day, on this day we are going to say it's 1 day to fail. On this day we are going to say 2 days to fail. On this day we are going to say 3 days to fail. On this day we are going to say 5 days to fail. So what the model is going to predict is how many days are left, how many days of useful life is left for that equipment. The third one, which is actually which probably is being used, is a multi-class classification approach. In multi-class classification, we have multiple buckets, and how the problem statement will look like: predict the probability of failure of an equipment within next 3 weeks of time, or 2 weeks of time, or 1 week of time. These 3 to 1 are examples. I'm just giving an example. So predict the probability of failure of an equipment within next 3 weeks of time, or 2 weeks of time, or 1 week of time. So if this is the failure point, this will belong to one category. 1 week from the 1 week from the failure. This is probably 2 weeks from the failure, right? The second week from the failure. This is third week from the failure. Now, what is the use? Why do we want to use this thing? Because it gives more time to get prepared. The moment I know an equipment is going to, this is the third week before an equipment is going to fail, I probably raise a ticket. On the second week, probably I buy the part which is going to fail. And on the last week, probably I send the service person to service the equipment. So I have sufficient amount of time to get ready. And the last approach is, the problem statement in the last approach would be: predict that my equipment is going to fail in next 7 days due to a mechanical fault. Predict my equipment is going to fail in next 7 days due to a electrical problem. So the duration, the window size, X remains the same, but we have different categories based on different root causes. This is the case where we have introduced the root causes. How many categories we will have? Categories is equal to number of root causes. Predict the equipment is going to fail within next 7 days based on root cause PI. PI could be P1, 2, 3, 4, whatever the number of root causes. So these are the different types of these are the different ways in which actually we can convert a predictive maintenance problem into a data science problem. And this is going to be the first step. And it's not that we directly jump into the more complex problem. Probably we should start with a very simple problem, which could be the binary classification problem. Okay, and slowly we see the success, we find out the patterns, and then slowly move into a complex problem. Even in normal software development, we build a prototype object first, we build a very naive product first, and then we develop. So now there are regression approaches and there are classification approaches. What we should pick up, this is from my experience. If the business permits, if the problem statement permits, always prefer classification over regression. We can think about regression as a classification with infinite number of classes. So classifications are always easier to implement, easier to maintain, and easier to understand. It's so given with the problem of predicting temperature tomorrow, or predicting whether tomorrow is going to be hot or cold, prefer for the classification. Say to the business, okay, well, is it okay if I just predict if tomorrow is going to be hot, cold, or normal? Now, why it is a time series classification? This is actually a time series classification problem. This is a time series classification problem because the data, we are going to predict the health of an asset or an equipment based on the health of the equipment in the past. And the health data, it depends on the time. So the most impacting features, the most significant features are related to time. So this is a time series classification problem. We have a there is actually, this is like a completely different what should I say? It's a different area which is being where people are focusing in the machine learning industry, like computer vision, natural language processing. There is time series. Within time series, we have time series forecasting and time series classification. So the particular problem which we are dealing here is a time series classification problem. Now, so we now know how we have to convert a machine learning business problem into a data science problem. Now let's start taking into start looking into the other things. Okay, first is data. This is from a paper from Google about hidden technical debt. So if you can see, actually in a production system or in a real software system, the machine learning code is a very small component. There are a lot of other components which needs to be there, and out of these components, data related components are occupies a significant portion. Because in machine learning, if I have good data, probably a weak learner, if I have good data, probably a weak learner can weak learner or weak algorithm can produce a good quality model. But if I have a lesser amount of data or bad quality data, then probably a very strong algorithm, even a neural network or deep learning, can't also make sense out of it, can't build a good model. So data is very important. Now for our predictive maintenance, we need to know, okay, I want to predict the health of an equipment in future. What kind of data should I use? So who will be able to tell it? Of course, we need to talk to the domain experts. There is a possibility that the company who is doing who is trying to do predictive maintenance using machine learning may already be doing predictive maintenance based on the rule-based thing. They already have a sense of the data. They are already gathering the data. So once we talk to them, we'll find out that, well, this kind of problem can be solved with this kind of data. Well, one thumb rule for any machine learning problem: with given amount of data or given type of data, if a human being can't solve that problem, maybe intuitively, with that particular set of data, a machine learning model can't also probably solve it. So we have to have relevant data. Now, once we know what types of data we need to have sufficient amount of data. I want to predict the failure of an equipment 7 days in advance, but I have data for only a month for a particular equipment. Is that sufficient? Probably no. I want to predict the failure of an equipment during the winter months. I have summer months data. Is that okay? Probably no. Well, I have an equipment's data, but I don't have any failure history. How the model will learn how the failure pattern looks like? We have to feed them. That's why supervised learning. That's where I have to help the model to learn the pattern of failure. So I need to have large number of failures. I should have sufficient amount of data. And finally, the quality of the data. All this health data, they are from IoT devices. They are collected through sensors, traveled over the internet, and finally they are sitting in my server, in my database. So there could be problem with the data. If the quality of the data is bad, the model produced would be bad. Garbage in, garbage out. I can't make a good quality model with a bad quality data. Now, data collection. What are the exact types of data which we need for solving a predictive maintenance model problem? So broadly, it has two categories: temporal data, that means the data which has time as a component, and the static data, which doesn't have time as a component. So first thing is, of course, equipment's health. I want to predict the equipment's health in the future, so I need to know the equipment's health now, right? Examples probably vibration, voltage, temperature, humidity, pressure, etc. Right? And these data information are mostly collected over IoT sensors. These are the time series features which help the algorithm to learn the normal or healthy patterns and unhealthy patterns when the equipment is doing bad versus when the equipment is doing good. And then the maintenance history, when the equipment was down, what was the repairment, what was the problem, what kind of repair was done, which components was replaced, all these things. It helps me to understand the degradation pattern. Failure history, we are talking about predictive maintenance, but still the equipment may fail abruptly. I need that kind of data. Weather, the humidity, the temperature, outside temperature, they contribute to the degradation of the equipment. So I need to know about the weather. And there could be the load on the equipment. Say if I am predicting the health of an equipment, I want to predict the health of an equipment in a shopping mall, air conditioning system in a shopping mall. Probably there is more load when there are holiday seasons. So if I know that kind of information, which is not related to the health of the equipment, but probably something which influences the health, that's better. Then comes the static data. Static data is mostly about who manufacturer, make, model, when the equipment was manufactured, how old it is, and geographical location. The failure patterns in humid areas will be different from the failure patterns in probably very cold areas. Once we have the data, what we should do is data exploration and validation. It's not that once we have the data, immediately we can pump it to a model. We can't do that. We have to look into the data. We have to find out whether the data quality is good or bad, whether we are able to find out the patterns which we are expecting to see. So probably we can probably expect to see this kind of patterns. Okay, again, this is from a blog post, from a document from Google. So, so as the equipment gets older, probably the efficiency of the equipment goes down. As the equipment gets older, probably the heat generated by equipment goes up. Whether I'm able to see this kind of patterns. If I am not able to see some obvious patterns, probably I should go back, collect more data, or I should do something else called feature engineering, okay, which we are going to talk next. Now, once we have the data, right, we have actually data from different types of sources. We have the data from, we have the data about the health of the asset. We have the data, this is probably health of the asset. We have the data about the maintenance. We have the data about the parts replaced. We have the static data, equipment ID and age. Now we have to merge all those things. We can't feed all the data differently to a machine learning algorithm. We have to make a tabular kind of data out of it, and then we need to feed. Okay. So here, that's what we are doing. Say for example, on 13th of January, for equipment 1, this was the age 700 days, the temperature was 31, humidity 83. There was any maintenance? No, that's why it's 0. There was any part replaced? No. What was the label, healthy or unhealthy? It was probably healthy, so label is 0. What happened on 15th of January? The same equipment went unhealthy, so we have a 1 here. And but that day there was no servicing. On 16th of January there was a servicing. That means the maintenance activity happened, and we had to replace the circuit. Maybe that day that day also the equipment was not healthy. From the very next day, on 17th of January, the equipment become healthy. So that's how we start capturing the data, or we start putting together all the data. Similarly, we will have data for other equipments. So finally, each row here represents the state of an equipment on a particular day. And the state means its health, its maintenance, its static data, everything. And of course, the label. Now, these are the IoT data, right? These are all IoT data. And I think I'm running out of time. Okay, let me rush a little bit. These are IoT data, so there would be missing values. And if there are missing values, that means probably the temperature, today's temperature is there, tomorrow's temperature is not there. I need to fill that, correct? So there are different strategies to fill that. We can use something called forward filling. We can use something called domain specific some filling, like for example, Tuesday 1 p.m.'s data is not available. What I do is I pick up the last Tuesday 1 p.m.'s data and fill it. Okay. Similarly, we may have to remove the duplicates. There could be duplicate data as well. Now, this is little interesting. I'll probably take a little bit of time here to do feature engineering. So say I have temperature and I believe the temperature is aligns well with the failure pattern. But then I realize, no, it's not temperature. It's the square of the temperature which is aligned with the failure pattern. Now, if I feed the temperature data to the algorithm will not be able to calculate temperature square, or algorithm will not know that temperature square fits well. I have to do that. So I have to take temperature. I have to create a new feature called temperature square out of it. So that's what exactly happens when we do feature engineering. There are a specific set of features which historically which has been found to work well for predictive maintenance, machine learning in predictive maintenance. One thing is the data is captured over individual time units. Say the temperature is captured over every 1 minute or every five minutes. And generally it would be very noisy. It would be like zippy. So but the algorithms are not good when the data fluctuates very much. Algorithms needs a slow change of data to understand the pattern. So what we do is we have to do some aggregation mechanism to smooth the data. So for example, maybe we'll instead of taking every minute's temperature, we average the temperature over a day. And what we found out that as the machine degrades, the average temperature of the machine increases over time. Now we know that we have to do the aggregation, but do we need to do the aggregation over an hour or over a day or over 2 days? So there is a thumb rule. How far in future the model has to predict? I want to predict the failure of an equipment 7 days in advance or 15 days in advance. So that how far in future the model has to predict influences how far in the past the model has to look back. So if I want to predict probably in the days level, 7 days in advance or 15 days in advance, then I should probably aggregate the data backwards, historical data, probably over 7 days or over 15 days or over 21 days or over 30 days. But I may not need to do it in the month level, probably. If I want to predict the failure 1 month in advance, then probably I have to do an aggregation backward. I need to go deep. Maybe I need to do aggregation over a month, 2 months, 3 months, or something like that. This looking back period is called lag. We need to create a lot of lag features. So we know we have to do an aggregation. We know we have to use something called lagging lags. We use some mechanism called rolling aggregate. Due to the time, I'm going to skip it. There are other kind of aggregation mechanism also, which I have not mentioned here, but I have referred to all these things. If you are interested, please look at those. These one thing I should mention, actually, this entire slide is made based on publicly available data. There were two intentions behind that. Number one, I can't share anything which is company proprietary. And number two, since the community is the student community, I should give them the knowledge which is already available so that they can go back and they can learn from it. Now, do I need to do only average? I want to do an aggregate. I want to do take the average of temperature over last 7 days. That's going to be my feature. But should I do only average? No. Maybe what matters is not the average. What matters is a variance. As the degradation increases, the temperature becomes very fluctuating. So the variance of temperature for a day or for 7 days or 15 days, that may be a meaningful feature. Or the number of peaks of temperature or vibration, that may be a feature. So we need to apply the aggregation on different kind of statistical functions. Then the date itself could be a good way to build features. From a date, I can find out the day of the month, the day of the year, the week of the year, whether it's a weekend or weekday, the month, the quarter, etc., etc. That builds a sense, that gives a sense of time to the algorithm. Finally, maintenance data. What happens My personal experiences with all this health related data, right? We can build a model up to a certain extent. The model's performance goes to a certain extent. Then we need to introduce new perspective to the model, new insights to the model. And that's where maintenance data comes into play. So the day since failure, this is a very good feature. My equipment has failed and it was repaired yesterday. What is the probability that it will fail in next 7 days? Probably very less probability. It has been already looked into by a service person, but it may fail in next 6 days, right? So that could be a good feature. Or my equipment has failed because of an electrical error and it has been maintained. What is the probability that it's going to fail because of a mechanical issue or a completely different issue tomorrow? Yeah, it could be possible, right? Because the service person who visited, he probably didn't look into that particular area of that part of that equipment. So maintenance data, using maintenance data, we can create a lot of features. Remember, feature engineering is a way in which you are exposing the patterns, you are guiding the algorithm to understand the pattern. You are basically helping the algorithm to see what it can't see. Now, model and architecture, I'm not going to talk about this. This is very, very experimental. Machine learning is an experimental thing. Here, there is no best practices about modeling technique. I can't say, well, for my data, tree-based models worked well. So for your data also, tree-based model will work well, although we are solving the same predictive maintenance problem. That may not be the case. So we have to try with different algorithms and we need to see what works for which data. However, this chart comes from again Google's recommendation, where they are talking about different specific deep learning algorithms, neural networks, and tree-based algorithms. But in general, what I suggest is for any machine learning problem, in any machine learning problem, when you start, probably it's better to start with some kind of gradient boosting machines, XGBoost, LGBoost, at least some kind of random forest. Start with that and then slowly, gradually increase it to a different thing. And one more thing I should mention, that what happens in industry, a complex model is not always preferred. We probably want to build a model which is simpler, which is easy to build, easy to maintain, and easy to uh, understand. Because if my model works, doesn't do a proper work, that means if my model makes a false prediction, the business and customers will come back to me and say why this prediction was made, and I have to explain it. Otherwise, even the business will not be confident on me if I can't explain a particular prediction. So interpretability is a must in models which are built in industry compared to probably the research space. In research space probably mostly the performance of the model gets highlight. Now, I know I have this data, I know I have to build the model, I know these are the algorithms, but how I'm going to validate it, right? So what happens is, say I am given with 2 years data. What I'm going to do, I'm going to separate out 6 months data completely. I'm not going to touch that data at all. I'll take rest of the data, and using that data, I'm going to build, I'm going to do the training. Once I'm happy with the model which I have built, then I'll use the test data. Now, even while building the model, it's not just that I dump the model onto a algorithm and the model comes out. We need to do a lot of tunings. There would be knobs which can be tuned. So I need to tune those knobs. And for that, I have to run a lot of experiments. So how do I validate the results of those experiments, whether I am tuning in the right direction or not? That's where we use cross validation. So this is the approach which is used in a normal machine learning problem, not in predictive maintenance. What I do, instead of building one model, I probably build multiple models. Now, while building the first model, I take 4 folds. Using those 4 folds of data, I build a model and predict on 1 fold. In the next step, I build the model on these 4 folds and predict or validate it on this fold. This way, I probably build 5 models. Then I take all the results, performance metrics. I then aggregate and then I say, okay, this is the performance of the model. Okay, now 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 why this approach works well? Because here what is happening is, um, here all the data, if you see, all the data is actually getting used to train the model as well as to test the model, so that the model which gets built generalize well. So this is again a huge topic itself, overfitting, but this gives you some idea. Now, in time series thing, which is our predictive maintenance, we can't do a random validation. So I can't build a model probably based on February, March, April, and May's data and validate it on January's data. I can't go back and say, well, oh, I have built a model for February, March, April, May. I want to predict whether an asset is going to fail in January or not, because that's not my goal. I probably want to validate the model on future data. So that's what exactly we do it here. We build a model on past data and we validate the model on future data. Again, there are two approaches, sliding window and expanding window. I'll request you to visit this link and read about it. Then there is another thing which is about split between training and test data. So there is a gap. I want to predict the date failure 7 days in advance. So that 7 days is basically a 7 days basically window of failure. Now, when we create this training and test data, we have to maintain the window. So that's where we split the data like this. Now, model evaluation, I know how to validate the model. That's the validation strategy. But what is the metrics? What is the exact formula using which we need to do the validation? This is where it is. We are running out of time again. I'm sorry about that. But two things I would like to mention. See, our case, that's a imbalanced data, right? Basically, what happens if I look into an asset's history, probably out of 100 days, for 99 days it was doing well. For 1 day it was not doing well. So the algorithm is not getting enough opportunity to learn the failure pattern. That needs to be taken care in mind when we build the model, when we choose the algorithm, and when it evaluate. And number two is the high cost of false alarm. We have, if we raise an alarm, if we say this device is going to stop working, we send it for maintenance, but actually it was healthy, then I have costed money to the company, which may not be acceptable. Even that can be just the other way as well. I can have a mechanism where if I raise a false alarm, there could be another mechanism to validate whether that's right or not. But anyway, just keep in mind, when we have imbalanced data, accuracy is not a good matrix. If you are doing machine learning already, you should always remember that. Look for other metrics which can be useful. Now I have built all the models. Okay, I have built the models. I have a good model. What I'm supposed to do, I'm going to put it in production. The new data starts flowing in. The new equipment's data starts flowing in, and I'm going to predict whether an equipment is going to fail within X amount of time. What is needed? While doing the prediction, I need to build the same set of features which I talked about, which I used during the training. Okay, and now there are different types of scoring approach. One is real-time scoring approach, which happens in Google Maps. In Google Maps, what happens is as we move every time based on the traffic situation, it predicts the time to reach my destination, right? But for our predictive maintenance, we don't need that kind of, generally we don't need that kind of real-time things. Here the model's decision may wait for some time. I'm going to predict whether an asset is going to fail in next 7 days or next 15 days or next 1 month. It's okay if I do it 1 or 2 days early or less, and 1 or 2 hours before or later. So what could be a suggested approach? Like I can do prediction for all the asset once in a day, and probably I can look into whether the asset is going to fail once in next 7 days. If the window is bigger, probably I can do the same thing once in a week or something like that. So what kind of scoring we use? We use something called batch scoring. Finally, we are in the last slide, but the most important slide. I have built a model, I have placed it in the production. Is my work done? Is the work of a data scientist or a machine learning engineer done? In a normal software industry, that's the case. Like once a product gets deployed, it's generally work. There would be bugs, but in a machine learning industry or data science industry, this is when the work starts. Because the moment you deploy a model in the production, it starts decaying, its performance slowly starts degrading. Number one, how I am going to measure the performance? I have to compare the predictions which I have made with the ground truth. I told that this equipment is going to fail in next 7 days. Has it really failed? When the service person visited the equipment to service it, did he find out that the asset, a part was really faulty or it was about to die? So I need to do that comparison and then find out the performance of the model. Now, another example, say I have built a model using the summer months data. Now the winter is approaching. The model's performance will slowly start degrading because the latest the weather is changing and the model doesn't know that pattern. So what we need to do, as the performance is degrading, we have to go back and we have to again retrain the model. So with the latest data, updated data, so it understands the latest pattern, and based on that, it again starts doing the prediction. So that's what you see here, that we fetch, clean, prepare the data, we train the model, evaluate the model, we deploy it in production, and then we start monitoring. The actual work starts here. Machine learning models fail silently. I predict that an equipment is going to fail 1 month down the line. So I have to really wait for 1 month for it to fail, and then only I'll understand. So we have to be very, very careful while evaluating. The evaluation process should be continuous. With this, my presentation ends here. These are the references. These are the references based on machine learning. First two are open source. These are blogs basically, or web pages. This is a book. Then for predictive maintenance, all the things are open source. This is a Azure Microsoft's guide. This is probably Google's guide, and this is a paper from the archive. Feel free to visit these links. For a machine learning beginners, I'll ask them to visit, of course, these two links. For a predictive maintenance guys, read at least these two pages from Microsoft and Google. That will give you a very good idea. That's it. And now I'm open for questions.
Thank you, sir. Thank you for your informative and insightful presentation. Now, can we start the question answer round?
Yeah, there are a few questions in the question panel, and sir, I have assigned you the questions. Can you see it, or should I read it out for you?
Yeah, I can see.
If you can see, fine. Otherwise, I can read it out. No problems with that.
Okay.
So it will be better if I read out. I think that is better. So let me go with the questions one by one. First question, yeah. Sir, Professor Shayok Pramanik has asked, sir, what roadmap should a student take to learn machine learning within a year?
Yeah, so first thing what I'll suggest is, see, the thing is machine learning is good, but probably knowing software engineering is better to get a job. Well, just because you know what kind of problem you want to solve, just because you know to build a model doesn't mean that um, you will be employed. So that's the job perspective. But if you ask me how should you learn, my answer would be not to attend very theoretical courses first, but to solving real problems. So Kaggle is a good place to start, and Kaggle has a lot of playground competitions. It's a data science competition portal. They have some very basic courses, like the courses which can be completed in 4 hours, a 4 hours course for learning Python, a 4 hours course to do the visualization. Do those courses, pick up a playground competition, start working on it. This is true if you are interested mostly about numeric or tabular data, which I talked about. Okay. Now, if you are interested about deep learning, that means you want to work mostly on computer vision and natural language processing, then there is a course called Fast AI. Okay, is my screen still shared? Sir, is my screen still shared?
Shared. Your screen is still shared.
Okay,
You can
and
see Google.
can
Google
you?
open.
Okay, so there is a course called Fast AI. I'll say that this course is very good. They are going to actually this is a free course, and you don't need to. But it's a difficult to follow course. Stick to it. They are going to launch a new session very soon, within probably next few weeks. They have a book which is openly available. Follow this, but this is particularly for deep learning. Otherwise, my recommendation is to learn by doing and do Kaggle for that. I don't know why it's not opening. This
So,
is the
Professor Shayok, yeah.
yeah. Please go ahead.
Okay, so Professor Shayok, I believe that you have got your answer, and Dibbo Chakraborty, I believe he's a student. He left a similar question, almost similar question, that how to learn ML quickly. So I think Dibbo Chakraborty also got your answer with that same question. So the next question comes from Dr. Shujit Kumar Bandopadhyay. He asks that how much AI and ML are interrelated. That is, whether processors of ML are needed also to learn AI, or the vice versa.
Yeah, so mostly this is what happens right now. If we want to, in today's age, in 2020, probably if we want to do AI, it would be mostly ML, right? We need to know the ML methodologies. Where is that? Yeah, we need to mostly know the ML methodologies. So for example, if we want to build a self-driving car, there would be mechanical things associated, but then computer vision would be an integrated thing. Without computer vision, the self-driving car cannot be built, right? So yes, machine learning we need to know, and mostly for human-like intelligence, we deal with the data like computer vision data, like image data or text data or audio data. In those things, deep learning has made a tremendous progress. So yes, we need to know about deep learning, machine learning to do a AI product in 2020.
Okay, so I think I have got your answer, Dr. Shujit Bandopadhyay. The next question comes from Vivek Chetri. He's a leading student member of this IETE forum. So he writes, a company needs both data analyst and data science person. So does machine learning bring both of them to a common ground?
Yeah, so the expectation from data analyst is little less. When you are a data analyst, probably the expectation is you spend a lot of time understanding the data, doing visualization, getting insight from the data. I'll give an example. I used to work for a small non-profit organization at some point of time, and they gave me a lot of data about their readers. So I spent some time, made a presentation, and I presented it to my manager. My manager said, okay, I see here you have a lot of data, but I don't see insight. Okay, so that's where a data analyst comes into picture. It's not about the average temperature probably over next few days, but whether the temperature is going up or down, something like that. So that's where data analyst comes into picture. The job is mostly to scrub the data, munch the data, play with the data, get an insight from the data. Now, to get the insight, if we need to use machine learning, use it, or probably build some small models to get more insight. That's why data analysts are mostly used. Whereas in data science, the idea is probably to build a product, at least in the industry, like you will be building a full swing product using data driven approach. But yes, to answer your question, both a data scientist should know data munging and machine learning. A data analyst should also know machine learning plus data munging, but the area of focus may be different. And mostly a data analyst is a junior role, whereas a data scientist is a kind of senior role. Probably that
I think
answers the question.
Vivek, Yeah, Vivek, I sure that you have got your answer. He has got another question, but I will take that question a little later because it takes to a different dimension, I believe. So I will take one question from Mr. Shom Shubro Shet. He is also a very good student of our university. Two questions he has left, and I read those two questions out together. Is there any algorithmic approach to choose which method of ML to apply? And second question, how can I understand that a specific application is suitable for supervised learning?
Yeah, so well, let me answer one by one. So in machine learning, if you listen to this first AI course, the author of the course, Jeremy Howard, he's a very famous guy. He says one thing: should I try blah? So I want to do machine learning. Should I try blah? Blah means probably some algorithm. The answer is you should try blah blah. Okay, so machine learning is very empirical in nature, experiment based in nature, practice based in nature. Okay, so theory may say that RNN works better or LSTM works better when it comes to time series. But probably when you pick up a problem, you will find out that no, LSTM is not working better. Even a time series problem may not work better with RNN or LSTM. I'll give some examples. So in Kaggle, if you go, there was a competition very recently. There was a competition called M5 competition. That's a forecasting competition, time series forecasting competition, which gets arranged, which gets participated by forecasters across the world. And the expectation was that, okay, maybe some deep learning architecture, complex deep learning architecture, that's going to win the competition. But what the person who owned the competition is a student from probably Korea, and he used a tree-based model. Okay, so to answer your question, there is probably some guidelines, there could be thumb rules, but if we want to find out whether a particular algorithm works for that particular data or not, you have to try and find out. The second question is, I think the second question, I forgot the second question. I think I
Can I
have it.
understand that a
Uh-huh.
how can I
Specific
understand
application
that a
is suitable,
specific
right?
application is suitable for supervised learning?
Yeah, I think this is the most complex part of doing machine learning. A lot of companies are hiring for machine learning nowadays, and their leaders, they probably don't know whether they have a problem which can be solved using machine learning. Again, I'll give an example. At some point of time, I used to volunteer for NGOs to find out whether they have a data-driven problem. They have problems which can be solved using data science. So we were talking to an NGO who works in the education sector, and they wanted to do machine learning, but they didn't have data, and the data which they had, they didn't actually have a problem which can be solved using machine learning. Okay, so there is no hard and fast rule. This is where you do a lot of brainstorming and find out whether you have examples, basically sample data, and you have the answers, basically the labels already available. If you have historical data like that, then probably you can build a supervised machine learning. So this is again something which you learn with practice. And of course, you can do Google search. You can try to find out whether other people are solving the same problem using some supervised approach. You can talk to your friends or seniors who are already working in the machine learning industry or data science industry. They may help you, but there is no guidance as such. It's all practice based. I hope that
So I
answers.
think Shom Shubro,
Som
you have
Subras,
definitely,
yeah.
yeah, definitely have got your answer. So next question from Dr. Sujit Bandopadhyay. In your opinion, sir, whether predictive maintenance will be cost effective compared to preventive maintenance?
Yeah, that's a very valid question. So in fact, when I started working on it, I have the same thing in mind, whether predictive maintenance and is better or preventive maintenance is better. So in a country like India, um, I think predictive maintenance doesn't matter. Okay, they are probably, it's all reactive maintenance. Here we all inform the service person only when it fails, right? But in industry, and especially in US and European countries where the cost of labor is very high, or the cost of the business itself is very high, their predictive maintenance is making an impact. So I know there are cases where just to raise one ticket, it costs around $1,000. Okay, so in India probably it would be, it may not be even like just to send the service person, it costs $1,000. In India maybe it would not cost 500 rupees, or it may not cost 500 rupees. So yes, in developing countries, in developed countries, predictive maintenance makes sense because they have a return on investment, but probably like developing countries it may not, but still an insight is always better, right? If we have a predictive maintenance system which starts predicting whether it's going to fail, that gives some insight to the customers. Probably if a hospital is a customer for air conditioning system, they will know, if they know that okay, this air conditioner is probably going to stop working, they will probably arrange another air conditioner or think about some other option. So yeah, that's the answer.
Okay,
I
so I
hope
really believe
that's
that again that has answered the question. Okay, there is one comment from Professor Chirodeep Mukherjee. He's the faculty coordinator of this IETE forum in UM Jaipur. So I just read out his comment. Sir, you have exactly shown the mathematical operations which we can use in feature engineering. It was really useful. There are many such comments, but I really felt this is very nicely written, so I read it out. There are many other thanks giving to you, sir, for the nice presentation. I take up a question from Aditya Ray, which it may be a good question for the students who are listening to this and learning it for the first time. He asks from you some reference of books which students, if needed, can use. Apart from the links that you have given, if you can suggest some books to start learning AI and ML, if you can suggest some books, that is what his question is.
Well, I'll say I'll probably okay, this
Hello?
is a book. Yeah, can you hear me?
Hello.
I can
So you
hear
got
you.
inaudible.
I can hear you. Can you hear
Hello.
me?
Suddenly, I think you got muted or something like that. Just let me check once.
Can you hear
Yeah.
me?
Now I think you are okay.
Okay.
Hello.
Okay. So can you hear me? Hello. Can you hear me?
Hello.
Hello. Can you hear me now?
Yes, sir, we can hear
No, you
you.
are not audible, sir.
Yes,
Okay. I
sir,
think.
we can hear you.
Okay. Okay. So that's fine then. So in that case, this is actually a book. Okay. Hands-on
Okay.
machine
Okay. You
learning
can
with.
continue. So I think, yeah. Hello.
Okay. Okay. No problem. I'm continuing. So this is a book, Hands-on Machine Learning with Scikit-learn, Keras, and TensorFlow. This is a good book on if you want to start on machine learning. Then there is a recent book which has come up, which is about deep learning using PyTorch. Okay, PyTorch, which is available for free again. Yeah, this is the book. If you do a Google search, this is available for free for the time being, so you can read that. But again, I'll say probably along with reading the books, go to Kaggle. They have something called courses. Okay, they have these Python courses, intro to machine learning. They have a lot of good small courses, short courses. Try to attend those courses. Then go to Fast AI. They have a good course as well. Attend those courses. The advantage is both for Kaggle and both for Fast AI, there is a very good community online forum there. So you can ask all your questions there and people would be happy to help you. One more thing I would like to mention, okay, I'm available over email and in Twitter here. So if you have any further question in future, you can probably reach to your sir, Chirodeep sir, they can forward me the questions, or you can directly feel free to directly reach out to me over these avenues, email and Twitter. I'm available there.
Thank you, sir. I will just take the last question from this from Vivek. I did not take that. Prior to that, one question which I think might have been answered, but still some little insights. So this is the last but one question.
Yeah.
The question is from Hanuman Kumar Singh, asking that can AI and ML engineer, alongside being AI and ML engineer, be a data scientist parallelly? So I think that's an interesting question. It is absolutely up to the person whether what is he's good or not. But still, because the question has been intended towards you and he is a student, I just did not leave out the question and placed in front of you, sir, for your thoughts.
Yeah, that's a very challenging thing. That's the data science industry is evolving. For example, where I work as a data scientist, but there are only 2 members in my team, me and another person. So we do all the stuff. Okay, if it is a machine learning engineering stuff, that means building machine learning pipeline, deploying the model, monitoring the model. We write the code for that, and we build the models as well. But whether that's going to work out for all the companies, probably no. Say for Google or Amazon, they can afford bigger teams. They can have separate teams for machine learning engineering, as well as they will have separate teams for data scientists. So it depends again on the company who is recruiting, their recruitment policies, their structure, funding, etc., etc. For an individual, at this point of time, probably it's possible, whether especially if you have a good software engineering background, you know coding good, you can always do machine learning engineering, and then you learn machine learning, deep learning, you can become a data scientist. But whether that's going to be the trend in future, we don't know. There is another possibility that in future we'll have a lot of ready-made models available, which has started happening already. So in that case, probably the job of the data scientists will come down. So we'll have already computer vision models available, which needs little bit of fine tuning to solve my problem. So in that case, maybe the more work would be more on the machine learning and less on the data science portion. But these are all possibilities. I really don't know. So I unfortunately don't have an answer whether you should learn both, whether machine learning and machine learning engineering and data scientists, these 2 positions will coexist in the same, like the same person would be considered as both. I don't know. We have to wait and see. But anybody can learn both. That's for sure. Whatever Sir said, right? That's for sure. You can learn both.
Yeah, thank you. Thank you so much, sir. I think Hanuman, you have definitely got your answer. So the last question, this one from Vivek Chetri, which I left out at the beginning. It was almost said quite early. So there are lots of good saying about machine learning in the internet. Is there something that you fear about harmful effects of machine learning to mankind? So
Yeah, this is actually, sir, you were saying something.
yeah, so I believe that this is the last question. So you may kindly take it, sir.
Yeah, sure. So this is actually a very good question. As an individual who practices machine learning, I am also a little worried. So there are trends which show that the machine learning is being used for various racial things. If we go back at some point of time, Microsoft built a face recognition application, and the data which they used was all from all white people, and probably they have some animals data as well. So when they tried to predict tried to recognize the face of a black person, the model said it's a chimpanzee. So that kind of bias, like we human beings, we are building the AI system, and if I have a bias towards a culture, bias towards a religion, bias towards a color, bias towards a nation, probably that will get reflected in our models. Okay, so that's one aspect of it. Fortunately, the pioneers in the industry, they have started talking about bias in AI and ML models. So in future, maybe the use of AI and ML would be controlled. For example, recently Microsoft has come out of all the face recognition applications or the startups in which they invested for face recognition, because that's not a application which should be used, they believe, and which is a right belief. So these kind of things will happen. But whether there are further risks, yes, there are a lot of risks. Slowly, where things are going into, as I was saying, right, if you read about GTP3, you will find out that a lot of work is going to be going to get automated. So it's slowly gaining human like intelligence. It's not yet human, it's like a more like a child now, but probably there will be a lot of automations, and which will start impacting uh, the uh, the especially developing countries like us, where there are a lot of manual works. So they don't need manual works. Say if a call center can be replaced with a chatbot, then why they will have a call center in a cheaper country? So now what is the way out? Should we stop the technology? That's not the way out. Should we control it? Probably. But then what is the way out? The only way out is to educate the humans. So if I am given with a control, what I'll probably do, I'll start educating students even in their early years, in their primary levels, with the skills of coding, so that in future they can start building new applications which will help the mankind in doing things which were not possible earlier. If we can focus on applications, say for example, a not face recognition application, a computer vision application, where you take a photo and it immediately tells you what disease you have, um, just by looking into your body, some marks, etc., etc., or what a doctor does, that kind of thing with an app, that would be helpful for countries like India. Here we don't have sufficient amount of doctors. So I'll probably say that our kids, our young generation, should start educating themselves with coding. It's like, if I need to do I need to learn a new language in 2020? Yes, you need to learn a new language. It may not be French, or it may not be Spanish. It would be probably Python or Java, because yes, the time which is waiting for us, that we don't know what's going to happen. AI has a lot of bad impacts. Read about GPT-3, read about face recognition, read about AI bias. You'll find out how can we stop that, how can we take advantage of the technological growth, is by educating ourselves. We can't really stop the progress of technology. If we stop as a country, as a society, somebody else will make the progress. I hope that answers.
Yeah,
Finally,
that
I want
was
to,
really a wonderful answer.
yeah, actually, I'll recommend another book. There is a book called 21 Lessons from 21st Century. If you get opportunity, read this book. The first chapter of the book exactly talks about this problem. Yeah, that's
That,
my answer.
that's a very good takeaway. So in fact, this really sounds very interesting. 21 lessons for the 21st century, and I will
Yeah,
definitely read this book. Read this book definitely. I will read
sure.
it.
Thank you, sir.
So thank you so much, sir. It was really a wonderful session, and the last answer was really brilliant. It was really I got a lot of insight from that. So Tisha, if you have any closing comments, so we are waiting for you. Yeah.
Yes, sir. Yes, sir. So thank you very much, sir. Starting from machine learning definition, you have focused on several applications where we can implement machine learning. Then you have shown us the examples of machine learning. Moreover, you have shown the types of ML system, that is supervised, unsupervised. Then you have shown the types of ML systems. Then you have describe predictive measurements as reactive, preventive, and predictive maintenance. You have explained the water filter example for refractive, preventive, and predictive maintenance in a very simple manner, sir. Then you show the root cause upon which predictive maintenance can be used. Then you have discussed regression and multi-class classifications with proper examples. Then you mentioned a very important point that if business permits, then classification is preferred over regression. Then we learned that a machine learning algorithm occupies a lower set in data recruitment, while the other services like quality data collection, data verification, process management, configuration, machine resource management, etc., also plays a crucial role. Lastly, you have emphasized on performance matrices of model evaluation for binary classifications. I'm very much sure that this webinar added value to attendees and listeners. Once the pandemic over, we'll invite you to our university, sir, so that we
Sure.
can have more relevant knowledge and encouragement from you. Thank you, sir.
Sure, sure. It was very good to interact with all of you. Especially thank you to your IATF chapter, our respected sir, Chiradeep sir, everybody. And thank you for bearing with me for such a long time. Right? It's like I have taken 2 hours. So, and thank you for the invitation.
Learn for 2 hours also.
Yeah, thank you. Thank you. I'll make
So
sure
thank
that
you.
this
Thanks.
PPT, yeah, I'll send this presentation so that it can be shared with the students, as well as I'll probably post it into Twitter so that you can also access. And feel free to reach out to me if the students have any question.
Thank you.
Thank you,
Thank you
sir.
so much, sir. Thank you so much. It was really, really a
Thank you.
wonderful session. And thanks to all the attendees out there. Thank you so much. Thank you.
Thank you. Thank you to everybody.